have mislaid the copy. Soft copy to the group.
You just enter? No. Okay.
You have to show it to you. You can check. You don't have the copy any longer. So we stopped at number 20, right? So let's move on to the next one. Let the vector field V equal to blah 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 be situated in a Cartesian system of coordinates with standard basis RJK. The value of constant alpha for which B is irrotational is, that means we want to establish that B is irrotational for some values of alpha. We take its curl and equate it to 0. You see what value of alpha will make that possible. So take the curl of vector V. This is I J K del del x del del y del del z. I have these to be x minus y squared 2xy alpha minus 2 minus x y. Okay, so let's do this together. We're going to equate this to irrotationality. This will be equal to 0I plus 0j plus 0k. All together, please. So you can take the x component of this, this will be down the y of this. That will be 2xy a minus 2. Does that make sense? When you differentiate this partially with respect to y, you get that. And differentiate this partially with respect to c, that is minus. That's going to be minus with respect to b, 2xy. This is what I have for the x component. And I take the next one, minus j into this. So to cancel this, we will have del del x of this. That is x. That is going to be y squared into a minus del del z of this. This is going to be minus y squared. That makes sense. This does not carry this. A is the constant. Y squared z, when you differentiate with respect to z, that's going to be minus y squared. Then you have plus, cancel this or cancel this, del the x of this, that will be 2yz minus del the y of this, that is minus 2yz. So I take this to 0I plus 0j plus 0k. Right now, this is going to give us this. I have 2xy right here. I can move it out.
Max. Now if x plus y squared z now.
So b
for other components of b.
Inside component.
Yes. Yes. For the matrix.
Okay, ax plus. I think it's minus. Minus y squared. Yeah. For the last one, del the y of this minus 2y. It's going to give me x, y into this will be a minus 2 minus 1. Does that make sense? You understand that? A minus 2 minus 1. Then minus j. Y squared is common to this. I can move it out. I can do something like minus y squared j into. This is going to give me a minus minus 1. Does that make sense?
Yes.
Okay. And then the last one is going to be plus, okay, this one's 0 plus 0 equals to 0I plus 0J plus 0K. So, obviously, this coefficient should be 0. I mean, for this x component to be 0 and for this one also to be 0, the coordinate should be 0. That means that a minus 3 should be equal to 0, which means a should be equal to 3. That is that about that. So the correct option is what? 21. B is the correct answer for 21. B is the correct answer for 21. How far now? Just go. Number 22. If z equals to 2y sin x I plus blah 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 is a vector in the three-dimensional Cartesian system of coordinates with standard basis I, J, K, find the curl of curl C. So how do you get the curl of curl C? That means you want to get nabla cross C. Abi? What does that give me? So you guys, I remember how to do something like this. It's going to be nabla of nabla dot C. I remember this minus nabla square of C. I remember something like this. Yes. Okay. Grad of div V. We talked about this the other day. Grad of div V minus Laplacian of V. I remember that. Okay. I remember this identity. I think it's part of this question also. That's what you have in question 14. Can you see? Question 14, number 2, identity here. When you have nabla cross U, you can do something like this to help you simplify your work. You can also do it normally. Which of them will be faster? You can do it this way and get your result. You can also do it one after the other. This one can be done and get your result. Anyone you do, you still get the same result. But I think this is long by we're going to be doing it in 2 parts. So you can just do nabla cross C. Nabla cross C is going to be equal to number 22. Nabla cross C is going to be I, J, K, down then X, down then Y, down Z. And then I have this to be 2y sin x, 4x plus yz squared, and z squared e to the power y. Is that correct? 2y sin x, 4x plus yz squared, and z squared e to the power y. This is going to be I into, we're going to cancel this and cancel everything of this with respect to y is still z squared e to the power y. Everything of this with respect to z, that's minus 2y plus j. I'm taking plus now. This is going to be ashamed of your ring. I'll take the everything from this with respect to z. I'm minus 0. I'm doing this now. Everything of this with respect to x minus. I'm going to have plus k into this to cancel this. Delta x of this, that is 4. Delta y of this, that is minus 2 sin x. That is that delta. So you just have to be can now take the curl of this. So I'm going to have curl C is equal to I J K. I'm going to have this to be L, then X, del, then Y, del, then Z. This is going to be Z squared e to the power Y minus 2y and this is going to be 4 minus 0 sin x. This is going to be I into cancel this and cancel this. The rest of this with respect to y 0 minus 2 cos x. We have minus 2 cos x minus derivative of this with respect to z. That would be 2z e to power y minus 2y minus 2y. That's the derivative with respect to z. Then we take the last one plus k into derivative of this with respect to y. That is derivative of this with respect to x is 0 minus derivative of this with respect to y. That would be z squared e to power y minus derivative of with respect to y. That's the minus 2. That would become plus 2. Do you understand what I've done? Alright, so that is going to be your final answer. Then look at the minus. This is going to be 2. Going to have 2 into cos x minus z squared. This one becomes plus minus z squared minus z to the power y plus y. If you want the minus becomes plus, and then this becomes minus. Mochi, sorry, please, let me check. Minus of and the minus multiplies over here to become positive, and this become negative. Then the last one, we're going to add this to the plus 2z minus z squared e to power y. Is there anything like that for the option? Okay. Option A is the correct one here. Same thing with what we have on the board. Number 22 is A. Number 23. If R equals x r plus yj plus zk, r squared equals x squared plus y squared plus z squared, f prime of r equals f dr. Then nabla of f prime of r is equivalent to, so how do you get the nabla of f prime of r? Nabla of f prime of r. Okay. That means this is going to be I del del x of f prime of r plus j del del y of f prime of r plus k del del z of f prime of r. Does that make sense? Alright. So we know that f prime of r, so if you want to get, you can get one of them and generalize for the other. Is that clear? You know that in this case, you have f prime of r. F is a function of r. So, if I want to differentiate this with respect to r, if I have something like f r. So, and I want to get this, I want to get the derivative of this with respect to s. I know that I can get Alright, let's continue. Hello, look at the board, please. So what are the differentiations with respect to x? Like I said, you can pick one of them. It's going to be del del x of f prime of r. Where f prime of r simply means the derivative of f with respect to r. I've been told that f is a function of r. Please listen. F is a function of r, so derivative of f with respect to r. I can also write it as del f del r, for instance. If I write that del f del r, it doesn't make any difference. When you use the del notation, it simply means that you are recognizing the fact that the function depends on other variables, aside x, for instance. If I write del f del x, since I'm taking the partial derivative with respect to x, I'm picking every other variable constant. That is recognizing that I have the function to be dependent on x and other variables. Okay? But I know that this function is dependent on only r. Okay? So if I write del f del r or the f r, they essentially mean the same thing. Do you understand what I just said? Okay, because it depends on only r. If I want to get the derivative of this, so it means that I'm interested in getting del x, please pay attention, of this expression, so which I can write as del f del r. Okay? That means this is what I have. I've differentiated this function f. I don't know how the function is defined, but that's not important here. So I want to differentiate with respect to x. And just like we've done previously, can you remember when we differentiated, for instance, the other thing we obtained lambda of r raised to power n. Can you remember something like this? Can you remember this? Okay, this is an example of such a situation. I have this to be some function of r, which is equal to r raised to power n. And for us to get the partial derivatives, we did something like this the other day. We did del r raised to power n del x. This was equal to del r raised to power n del r. That is differentiating with respect to r, abi, and use the chain rule to get the derivative multiplied by del r del x. Does it make sense? Do you understand this? Do you understand this? Okay, this was how we got the derivative that day. Can you remember that? Are we together? Okay, so yeah. See, look at something. Forget about the prime for a moment. If you don't have prime here, okay, if something is a function of r and you differentiate it, the function is still, the result is still a function of r. The derivative you have obtained is still a function of r. Does that make sense to you? You get that? So you will treat it the same way you will treat just a normal function of r. So if I want to differentiate this, I will just write this as del r of del f del r. Then I'll multiply the result by del r del x. Does that make sense? Do you understand this? Chain rule, just like what we've done here. Differentiate this with respect to r because it's a function of r. Then multiply by the derivative of r with respect to x. You know, by your chain rule, this regards to this, we are going to have the same thing on both sides. Does it make sense to you? Did you get that? So I want to differentiate this derivative with respect to x. That's the same thing as differentiating first with respect to r. Then multiplying by the derivative of r with respect to x. Is it clear? Is this clear? Okay. So that is going to give us this. So it's the same thing as differentiating this function with respect to x. But now we want to do it separately. So this simply means what you have here is going to be, so this is the same thing as del square r f and r squared. Does that make sense? When I put this and this together. Is that clear? Okay. Then multiply by del r del x. I know del r del x is x over r. Is it clear? Do you understand that? So similarly, if I want to get the other components, I'll see that similarly del y of del f del r is going to be equal to del square f del r square multiplied by y over r, and del e of del f del r is going to be equal to del square f del r square e over r. Does it make sense to you? Do you get this? Is it clear? Why is everybody quiet?
Clear.
Okay. Okay, look at something, please. Look at this. If you have, please pay attention, pay attention. This is what we mean by it. Assume that you have something like f of r equal to r squared. Listen very well. If you have f of r equal to r squared, you're going to have this to mean that you have del f del r. Sorry,
Bless you.
please listen very well. You know that if I have something like this, normally if I want to take total differential, the f, total differential, the f should be equal to del f del r multiplied by the r. Does that make sense? Have you seen this before? From partial differentiation.
Yeah.
You can remember this.
Yeah.
Why are we writing only one? Because f depends on only the variable r. Is it clear? Are we together, please?
Yeah.
If f, for instance, was a function of x and y, we would write the f, which is the total differential, equal to del f del x dx plus del f del y dy. Does that make sense? Is it clear? And if we want to get the total derivative, let's say with respect to y, we want to get the f dx. In this case, the f dx is not the same thing as del f del x. Why? Because the function does not depend on only x. It depends on x and y. Is it very clear? If I want to get the f dx here, simply do something like this. The f dx will be, I'll have to divide this total differential by x, which is going to be the same thing as having del f del x multiplied by dx over dx. Is it clear? Plus, I have this as del f del y multiplied by dy over dx. Is it making sense? Is it clear? Yes. This will give me the total differential with respect to x. Of course, the x dx is 1. You know, so I can ignore that. Then I have dy dx. So that means that obviously the f dx is not the same thing as del f del x because it depends on more than one variable. Is it clear? You understand this? Yes. You understand this? Okay, so, but if I have only one variable, now, if I want to get the total differential of f, the f is going to be del f del r multiplied by the r. Is it clear? There is just one variable here that f depends upon. F depends on only r. So, if I want to get the f, it is going to give me this. So, it also means that if I need to get the f dr, that is going to be what? Del f del r multiplied by the r over the r. Is it clear? Is it very clear? Okay. So this tells you that, of course, this will cancel this. So this tells you that the f dr is the same thing as del f del r when f depends on only one variable, only the variable r. Is it very clear? Do you understand this? Is it clear now? Is it clear what I'm doing? Okay. So that's why I've written this way. Of course, we know that f prime of r is the f the r, but we know that f is a function of r. F depends on r only. So the f the r can also be written as del f del r. Is it clear? Why am I writing that? Why am I writing it this way? So that you can relate both of them. Okay. So and you know, I think the other part is quite straightforward. Product rule. So if, for instance, if you have something like this, you're going to have f prime of r to be equal to 2r. I mean, this 2r is itself another function of r. You understand what I'm saying at all? It's still a function of r. Let's say it is g of r. So if I want to differentiate it, I'm still going to treat it the same way I will treat this function of r. Is it clear? Do you get this? Okay. So, do you understand this thing now? Do you understand this one now? So we simply use product rule. So just like if I want to differentiate this thing here now, if I want to differentiate, let's say I need to get del del x of r squared. How would you do this? This is going to be equal to del r squared del r multiplied by del r del x. Do you understand that? Yeah, that's the way we are dealing with it now. This is a function of r. I'm differentiating in respect to x. So I'm going to use the product rule to relate that. So that's the same thing we have done here. This is a function of r. I want to differentiate with respect to x. I'll differentiate it first with respect to r, then multiply my result by del r del x. Is it clear? Do you understand this now? So what is del r del x? We've done this in the past. I mean, so it is x over r. Is it clear? So that's how we think about that. So we do something similar for the others. We're going to have all of this. So don't forget also, listen now. Don't forget that f is a function of r only. So if you do del square f del r square, that's the same thing as f prime prime of r. Is it clear? That's the second derivative of f with respect to r. Is it making sense? Do you get this? Okay, so that is going to give us this. So what I have here is just going to be f prime prime of r. Is it clear? Multiplied by x over r. Okay, I think this is written as f prime prime of r multiplied by x over r. This is written as f prime prime of r multiplied by x over r. This is written as
Y over R.
Sorry, y over r. Thank you. F prime prime of r multiplied by z over r. Does that make sense? Is it clear? Okay, so we can move on now. So we can put all of the results into this. So this is going to give you nabla of f prime of r is equal to the I. So when you differentiate with respect to x, you get this. You get this. This is going to be f prime prime of r multiplied by x over r plus j f prime prime of r multiplied by y over r plus k f prime prime of r multiplied by z over r. Is it clear? Do you understand this? Alright, so you can factorize now. You have r is common to all of them, f prime prime is common to all of them. So basically what you have here is going to be f prime prime of r all over r. Then you are going to have in brackets, what do you have in brackets? A plus zk. Is it clear? Do you understand that? Okay, that's the same thing as the vector r. Is it making sense? Does that make sense? Why is everybody silent like this? You see the options? You know how I came about r vector? Yes. When you factorize that, you are going to have xi plus yj plus zk in the brackets. Does that make sense to you? When you move out f prime prime of r divided by r, you are going to have xi plus yj plus zk in the brackets. Is it clear? Divided by r, I'm going to have xi plus yj plus zk. So that is f prime prime of r all over r multiplied by r vector. So I'm given that r is equal to xi plus yj plus yeah, option D. That's correct. Option D, number 23 is option D. Let's move on. The next number 24. Evaluate nabla cross nabla phi at the point D's if phi is equal to cos log blah blah blah. How many of you did that? How many of you solved that? Number 24. To get zero vector, Abi now, rotor of gradient is 0. Abi now, from the logo, rotor of gradient is 0. There's no need to solve it. You know, this is an unnecessarily complicated function. Even if you want to solve it, you should have known that something is wrong somewhere. Because you get that? From what, maths? As you solve it on the board, maths. Alright, number 25. We shall follow the doctrine about the vector r. That's the position vector r. We are seeing that lambda cross r is 0. Abi? Yeah. 0 vector. That means it is irrotational. So A is true. B, R is vector field. Yes, obviously. Abi now defines the vector for every point in space. Number C, R is solenoidal. Is it solenoidal? No. Nabla dot R gave us 3. Can you remember that? So it is not 0. So it is not solenoidal. Can you see that? Magnitude of R is a scalar field, obviously. Magnitude of R is square root of x squared plus y squared plus z squared, which is a scalar field. Is it clear? Because it defines a scalar for every point x, y, z that it gives. Is it clear now? Alright, so number 25 is C. It's not solenoidal. Number 26. The directional derivative of the function phi equals x, y, z at the point 1, root 2, 1. The direction of the vector I plus k is, so how do you get directional derivative? That is going to when I'm still alive. That's going to be not phi dot unit vector A. Can you remember this? That's going to give you this directional derivative. And then you substitute that particular point in the lambda phi. Is it clear? Right, so now we given phi equals x, y, z. Phi equals x, y, z. So lambda phi will be equal to I. When I differentiate with respect to x, I'm going to get y, z plus j differentiate with respect to y. I'm going to get x, z plus k differentiate with respect to z. I'm going to get x, y. So when I substitute these numbers, 1, root 2, and 1 for x, y, and z respectively, I'm going to get this thing to be equal to I into, this one is root 2, this is 1, plus j into 1, 1, plus k into 1, multiplied by. Does that make sense? You get that? When you substitute the points 1, root 2, 1, is it clear? So that means set x equal to 1, y equal to 2, and z equal to 1. What does this give you? This is going to give you root 2I plus j plus root 2k. Is it clear? So what does this give you now? When you dot it with unit vector A. What's the unit vector along A? A is given as, where is it? The direction of I plus k. So our vector A is I plus k. So the unit vector in the direction will be I plus k divided by square root of 1 squared plus 1 squared. Does that make sense? It's going to be I plus k divided by root 2. Does it make sense? Is this clear? Yes. Alright, so that means the directional derivative, lambda phi multiplied by this is going to be, I'm going to take this and dot it with this. That is going to give me root 2I plus j plus root 2k is dot 1 over root 2 into I plus k. Is it clear? So I'll bring the x components. This will multiply that. Root 2 divided by root 2, that is 1. Plus the j component, this one has no component here, that is 0. Is it clear? I'll bring the k component, root 2 divided by root 2, that is another 1. So the result is 2. Does it make sense? Is it clear? Is this clear? Is this clear? Okay. So that is what option. Option D. Number 26 is option D. Number 27. Let A equals xi plus yj plus zk and B equals yi plus zj plus xk. Then vectors A and B are respectively. So what can you say about vectors A and B? You should want to work them out, Abi. But we know about vector A. Vector A is position vector. Abi now, our usual position vector R. We know that it is irrotational. Abi now. So we know vector A is irrotational. So that means option A cannot be correct because respectively is added. You understand what respectively means? That means in the order they have been mentioned. Abi, vector A comes first. Is it clear? Then vector B. So the first sentence, the first word here will be descriptive of vector A. The second one should be descriptive of vector B. Do you understand what I'm saying? Yes. You know what I just said? Because of the word respectively. Is it making sense? Yes. Come again, sir. And I say something like, Olamide and Simzi are male and female respectively. You get that? Yes. That means Olamide is male and Simzi is female. You get that? Proceed to the other. I think. Do you understand what I'm saying? Respectively means you have to follow the order they have been mentioned. Do you get that? You assign the descriptive terms in the order they have been mentioned. Is it clear? So the statement is their vectors A and B are respectively. So that means the first word will describe vector A, the second word will describe vector B. Is it making sense? Is this clear? Hello, listen. Is this clear? You know, if the word respectively is not there, what do you think the answer will be? If the word respectively is not there, you know it's another question entirely. You know that? If the word respectively is not there, that means you are looking for a property that is common to both of them. Abi? Do you understand what I'm saying? So whatever I'm picking must be something that applies to both of them. But because the word respectively is there, I will pick what applies to each of them in that order. Is it clear? So I know that vector A is irrotational. So irrotational can also be said to be conservative. But then the only ones that have irrotational coming first are options B and C. Abi? So the other one says irrotational and solenoid, irrotational and conservative. Of course, irrotational and conservative can be taken to mean the same thing in this context. Do you understand me? Alright, so let's check for vector B. Can you take the curl of vector B? What does it give you? Curl of vector B. Nabla cross B. What does it give you? This is going to be I, J, A, del X, del Y, del Z. Vector B is Y, Z, X. Is it clear? So this is going to give us what? This is going to give us, just pay attention now, pay attention. I'm going to cancel I. Del Y of this is 0. And del Z of this is 1. Then I'm going to take the next one, minus J. Obviously, it's not a 0 vector. I mean, just want to confirm if it is a zero vector. I mean, now, it is not a 0 vector. Is it irrotational? Yes. Look at it. Sorry. Is it solenoid? Lambda dot Z. That is going to be equal to del X of the X component of this Y plus del Y of the X component of this Y component of this plus del Z of the Z component of this is X. Is it making sense? Do you understand this? So obviously this is 0. Is it clear? Yeah. That means that vector A is irrotational and vector B is solenoidal. Does it make sense? So that's the proper option to B. So option B is the one that satisfies us. Option B is the correct answer for number 27. Is this clear? Okay. Number 28. If A equals to that, find nabla cross A. We've done something like this earlier. Let's read it again. You can use that identity of the one we talk about divergence of graph P plus. Please listen out. Oh, sorry, gradient of graph minus the Laplacian of B. You can use that identity. It's faster. Nabla cross A is going to be I del X del Y del So, listen very well. This is going to be x squared minus y minus yc x plus z plus I cancel the del the y of this 0 minus del the z of this minus y minus j. This is quiet now, enjoy it. Minus this is going to be del the x of this 1 minus del the z of this 0 and then plus a. Okay, 3x z squared. I was trying to test if you were following. I was following. I was about to say something. I tested if you were following. You have to first check.
You go still make another mistake.
Now many I test for the work.
No, in this line, your teacher is allowed to test you.
Yes.
Within minutes. So this is going to be, let's do it again. I into this, we cancel this. We need to have del the y of this, 0 minus del the z of this, minus y minus j into del the x of this is 1 minus del the z of this. That's 6x. Then the last one, plus k
0
into this is 0 minus this is
0.
It's going to give us y I. Then we're going to have this be plus, the 6x z minus 1 j. Is that fair? So you can take the nabla plus nabla plus a. This is going to give us give us y, del del x, del del y, del del z. We're going to have this y, we're going to have 6x minus 1, and it's going to give us I into this, because this is going to give us 0 minus this with respect to z, that will be 6x. Altogether, the minus j in this because of this. With respect to x, this is 0 minus with respect to z, this is 0. We're going to have the last one. With respect to x, this is 6 minus with respect to y, this is 1. Things like that in the options. Things like that in the options.
Yeah, see.
When you type this up, it's minus 6x I plus minus 1.
Everything is
As we were saying, choose C from the beginning. From number 1 to 30, just C. So, okay.
Okay, C. C is 50%, Abby.
I did tell you. Wow.
And get C. That's a hint to. You can go to your exam and just pick C. Not C.
But if you are type different, though, don't be missing.
Actually, I used to do that as a student.
Why you lie?
I won't be saying if I don't pick up too much. I
She's asking what I'm doing.
won't be saying I don't pick up too much.
Each time I solve the problem and I can't get the correct option, I don't think of what I
lost
will ask myself, what do I want to score in this course? A, I'll pick A and B.
That was everything.
I just feel I know that I don't know okay. I don't know it. I was doing it right or wrong. I know I have listened. There's no option. Okay, now I have you one score. You don't score, you don't need to say anything. Okay, the last one. Okay, what did you call the correct option? C. Wow. A unit normal to the surface, e raised by x squared plus y squared plus ln x squared plus c squared plus cos y squared plus c squared equal to 4 at the point 1, 0, 0 is, how do you get the unit normal? That will be nabla phi, Abi, divided by modulus of nabla phi. Abi now? Alright, so you know that nabla phi is normal to that surface.
Mark.
You know my voice now. So this is going to be unit normal is going to be equal to nabla phi over modulus of nabla phi. Is that clear? Is this clear? Alright, so what is nabla phi? differentiate this with respect to x, what do you get? This will be 2x e raised to the power x squared plus y squared. Do you understand what I'm doing? Do you understand what I'm doing? When I differentiate the first part of it with respect to x, that will be e raised to the power, 2x. That means I'll have to multiply by derivative of the curve. Is it clear? Which is 2x. E raised to the power x squared plus that. Then when I differentiate with x, that will be what? That will be plus 1 over x squared plus c squared multiplied by 2x. Then the last one does not carry x, so forget about that. Is it clear? Then I'll pick the next one plus j into first part carries x, which will be 2y. So it carries y, e raised to the power x squared plus y squared. Plus the next one does not carry y, so forget about it. So move to the last one. Minus sine, that will be minus or minus sine. That will become plus sine of y squared plus c squared and multiplied by 2y. That will be plus. Then we'll go to the last one plus k into, this will be with respect to z. The first one doesn't carry z. The next one, 1 over x squared plus z squared multiplied by 2z. So that is going to be, sorry. Pick the next step, that's going to be plus sine y squared plus z squared multiplied by 2z. That is going to be plus that. Then we are going to evaluate these at the point 1, 0, 0. That means x is equal to 1, y is equal to 0, and z equal to 0. So let's put that right here. So number 5 at the point 1, 0, 0 is going to be this. So we substitute x equal to 1. So this is going to give us x equal to, listen out, this is going to give us 2. E raised to the power 1. Happy now? Notice y is 0. Yes. So that will be 2e. Is it making sense? That will be I into 2e. Is it clear? Then you substitute the same thing here. This is going to be 1 over 1. Happy? Then this is going to be 2. So that will be plus 2. Then we'll move to the next one. Plus j into, this is going to be 0. Is it clear? So that is off. Then we'll come here also. This is 0. So that is off. Is it making sense? When you come to the next one, so this is 0. That is off. This is 0. That is off as well. Does that make sense to you? So it has only x components. Is it making sense? Is this clear? Alright. So we want to get the unit normal at this point. So this is our number 5. So that means this is normal will be equal to this divided by its modulus. Abi? That's going to give you what? I. Does it make sense? Do you understand that? Its modulus is Abi now. So that is our answer. That is that about that. Option C has the correct answer. Okay. Option C again.
Most of you know when this one next time.
Okay, now see if we go through. I don't know. Number 30. Which of the following statements is not true? Which of the following statement is not true? Which of them is not true? The spin of a conservative field is 0. Spin is another word for coil and rotor. Did you get that? Spin is another word for coil and rotor. Spin, coil, rotor, they all mean the same thing. Is it clear? Spin. So when I say something is irrotational, I can also say it is spin free. Is it clear? When I say spin free, it means it is irrotational. Does it make sense to you? Alright. So the spin of a conservative field is 0. Is that correct? Is that correct? Is that correct? Yes. Oh, it's conservative field. Okay, we have seen this before, have we? We have discussed conservative field before. So that is correct. Number 2. Sorry, option B. The maximum derivative of phi occurs in the direction of lambda phi. Is that correct? Yes. Alright. The next one, the divergence of chord is 0. Is that correct? Yes. That is the divergence of rotor. Have you now? Right. D, all of the above. Is it all of the above? Eh? Eh? All of the above. All of the above. English problem. E is the answer. D is the answer. None of them is correct. Abi? D is correct. D is correct. Listen, please. The conservative field, listen. Conservative field naturally means that on that field, when you take line integral between any 2 points in the field, it is independent of the path followed. That is naturally the meaning of conservative. You get that? So the conservative field has the property that it is irrotational. That means that field has no curl when you take the curl of the field. Is it making sense? So it is not, listen please, it is not always so that when you have a field to be orthogonal, if you have a field to be spin free, it does not always mean it is conservative. But when a field is conservative, it is always spin free. Huh? When the curve, that is when a field is irrotational, it is not necessarily conservative. But when it is conservative, it is always irrotational. You get that? One of the keys. Like I said at the beginning of this class, these things actually have their geometric meaning, but I'm restricted in what I can present to you at this stage. For instance, all these things will be properly viewed when you actually do double integrals and triple integrals. You know that you know them. You'll be able to relate with them. When it is conservative, it is definitely irrotational. However, the irrotational field is not necessarily conservative. Thank you for. All right, so let's start the next part of this topic. The next part of the topic. No, we're still on vector calculus. But we have not. Yeah, just like curvilinear. So listen. When you hear the word orthogonal simply means mutually perpendicular. Okay, just like your Cartesian coordinate system, the XYZ coordinate system is what we have been using so far. For all the definitions we considered so far, I mean, gradients, divergence, curl, we have used the Cartesian coordinate system. That is your XYZ coordinate system. Okay, and you can relate with this XYZ coordinate system, where the unit vectors are I, J, K respectively. Okay? I, J, and K are the unit vectors in their respective directions. Now, I can have a general coordinate system. When I say orthogonal, it means that irrespective of the coordinate system I want to pick, now, if I want to use a different coordinate system, I will always have the axis or any point I want to pick, the direction. At any point I want to pick, the directions will be mutually perpendicular. Do you understand what I'm saying? Okay? That means that I'm going to define the coordinate system still with unit vectors, okay, which are mutually perpendicular. Okay, so you will also come across, or you may also come across something like this in this course. You will definitely come across this orthogonal. When you hear the word orthogonal, it also means mutually perpendicular, and in addition to that, it means that they are of unit magnitude. Okay? So when I say orthonormal vectors, that means I'm talking about mutually perpendicular unit vectors. Is it clear? When I say orthogonal vectors, I'm talking about mutually perpendicular vectors. They are not necessarily unit vectors. Is it making sense? Do you know the difference between them now? Orthonormal means I'm talking about mutually perpendicular unit vectors. Orthogonal means I'm talking about mutually perpendicular vectors. Okay? They are not necessarily unit vectors. Okay, so for instance, listen now. The vectors I, J, K. Okay, this vector I, J, K. I can say they are orthogonal. Have you now? Why? Because they are mutually perpendicular. I know the word, don't mean of mutually. Yeah. That means if I pick any pair, they will be perpendicular to each other. Is it clear? If I pick I and J, they are perpendicular. J and K, they are perpendicular to each other. Is it making sense? So I can describe this set as the set of mutually perpendicular vectors. That is, I can describe them as a set of orthogonal vectors. I can also say they are orthonormal vectors because they are also of unit magnitude. Is it making sense? Is this making sense to you? Okay, so when I'm using my XYZ coordinate system, I know that these unit vectors have very definite and constant directions. Okay? We know that I is always in the positive X direction, J is always in the positive Y direction, K is always in the positive Z direction. So, if I want to differentiate something, listen now. For instance, if I want to differentiate a vector, let's say I want to differentiate a vector and let's say I have a vector A given by A equal to, let's say, xi plus yj, and I want to get the derivative of A with respect to t based on parameter t or variable t. I will say that this is the same thing as I del x del t plus j del y del t. Am I making sense? Okay, but listen now. The reason why I'm doing this here and it's reasonable, it's correct, is because I'm dealing with vectors I and j which are constant vectors. Constant in that they have constant magnitude of 1, abi, and they have constant directions. I know I is always in the positive x direction, so the direction cannot change. J is always in the positive y direction, the direction that cannot change. K is always in the positive z direction, that cannot change. So they are constant vectors. So if I were to take their derivative with respect to any variable, the derivative will be 0. Is it making sense? Okay, so when I'm dealing with this kind of vector and I want to take this derivative, I want to get this, but I don't get it two steps. Generally, if I'm dealing with something like this and I want to get the derivative, I should want to use the product rule. Okay, that means if this were dependent on t and I also were dependent on t, that is, if I was not a constant, you know, I should use the product rule and say this should be equal to x del I del t plus I del x del t plus y del j del t plus j del y del t. Is it making sense? Is this clear? Alright, so this is the general result that you get from this idea if each one of them was actually dependent. But I know that I is a constant vector, j is a constant vector. So definitely this is going to give me 0 and this is going to give me 0. So that is why this thing is correct. Is it making sense to you? But there are other coordinate systems. They are also orthogonal coordinate systems. But they are not going to, the axes are not going to be straight lines. They are going to be things other than straight lines. That's why we say orthogonal curvilinear coordinates. Is it making sense? That means that the axes that define these coordinate systems will not generally be straight lines. Is it clear? So when I have such cases, it means then that my unit vectors in the direction of those axes will not be constant. Does it make sense to you? Unit vectors in the direction of those axes will depend on the points and halves. Is it making sense? Okay, for instance, I can have a coordinate system, a general coordinate system. This is just for illustration. I have a coordinate system where the axes are, let's say they are directed this way. This one goes like this goes this way, and this comes this way. This is the origin of my coordinate system, so to speak. Okay, such that if I'm at any point, if I'm at this point, for instance, and I want to get the unit vector on this axis, the unit vector on this axis will be tangential to this axis at that point. Is it making sense? By the time I get here, the same unit vector will be pointing in this direction. tangent to the plane. Is it making sense? So depending on my location, unit vectors will have varying directions because this axis is not a straight line. Unlike here, this axis is a straight line, so I know that the unit vector in this direction is always pointing this way. So here, the unit vectors have different orientations, different directions, even though they have constant magnitude of 1. They have different orientations. So I cannot afford to treat them the way I would treat unit vectors I, j, k. Is it very clear? Is it very clear? So we talk about those unit vectors. So basically, what we want to discuss under this part is to see how we can go from the Cartesian coordinate system to an arbitrary orthogonal curvilinear coordinate system. Okay? So we will consider different coordinate systems, which some of them you can already relate with them. For instance, the polar coordinate system. You have heard of polar coordinate system before. Abi? Yeah. We did that in MTH 104. We did MTH 104. I think you should have done it somehow, maybe in physics. Polar coordinate system, where you use r and theta to define position. Abi? That's a coordinate system that is different from x and y coordinate system. Is it making sense to you? Is it clear? So we also have its generalization. We can have it as a spherical coordinate system. We can also have what we call the cylindrical coordinate system. So we consider those ones one after the other. But we want to look at the general approach. How do we go from one coordinate system to another coordinate system? Usually, we will go from the Cartesian coordinate system to an arbitrary orthogonal coordinate system, another orthogonal coordinate system. So, for instance, look at the illustration of the example I just gave you now. If you have a vector defined in the xy coordinate system, this is a Cartesian coordinate system. Look at it now. We have something like this. Let's say we have some vector r, okay, defining this, and I want to define a point. Okay, let's say I want to define this particular point. I'll be interested in x and y. If I want to define the position of that point, I will be interested in its x coordinate and y coordinate. But if I want to use the polar coordinate system, I'll be interested in something else. I'll be interested in what angle does it make. Abi? That will be some angle. Let's say angle theta. Do you get that? That is what angle does the line that joins it to the origin makes with the positive x-axis. I'll write it down as angle theta, and I'll find out what is the radial distance of that point from the origin. That is what we call I. That means that for every point x, y that I have on the Cartesian coordinate system, I can get their equivalent coordinates r, theta in the polar coordinate system. Does it make sense to you? Do you understand this idea? Okay, for instance, if I have this point, let's say this point is 3, 3, I can also express it in the polar coordinate system. So if I have a point 3, 3 in the Cartesian coordinate system, I will be interested in its coordinates in the polar coordinate system. That is going to give me what? R. So my R is going to be what? Square root of 3 squared plus 3 squared. Abi? Okay. Let's say we have 4 and 5. Something that we can easily get a whole number. 4 and 3. Let's say 3 and 4. Square root of 3 squared plus 3 squared. That's going to be 5. Abi? And then we're going to get theta. Theta will be the angle that this makes with the x-axis. Abi now? You can get that as tan inverse of. So theta is going to be equal to the tan inverse of. What is this going to give us? Y over x. So this is going to give us tan inverse of y over x. So this is going to be tan inverse of whatever y is. Y is 4, and this one is 3. So we're going to get that in radians. Don't worry about getting that. So whatever it is, so we can put that here. Let's say that is 1. So that means that this point in the Cartesian coordinate system, okay, is 3, 3. In the polar coordinate system, it is 5, theta 1. Is it making sense? Is it clear? So similarly, if I want to get a derivative, let's say I want to get derivative del x in this coordinate system, I will also be interested in how can I get something like del r, for instance, in this coordinate system, or how does this relate to this coordinate system, or if I want to get del theta in this coordinate system, how do I get it? For instance, if I want to get the gradient, or I want to get nabla, I know I'll be interested in del x and del y. Whereas in this coordinate system, what I'll be looking at should be del r and del theta. So how can I be sure that I will capture the same information as I would with del x and del y by using del r and del theta? Is it making sense to you? So to do this successfully, what we'll first do, So generally, if I want to go from the Cartesian coordinate system, which is defined by the coordinates x, y, z, and to a general orthogonal coordinate system defined as u by coordinates u, v, w. That means u, v, w is arbitrarily used for the coordinates u are the coordinates, the three orthogonal coordinates you have in the new system. Does it make sense to you? Just like I have here from x, y to r, theta. So u, v, w is representing a general coordinate system. Is it very clear? So one of the first things you will do here is, if now listen now, as you know that, for instance, if you have 5 and theta, how would you be able to obtain that? If you have r and theta, how can you obtain x and y from it? You know, basically what you need is, you need to know how the definition of the terms here actually relates with the Cartesian equivalence. See, do you understand what I'm saying now? That means, for instance, in this case, I know if I want to get the x coordinate is the distance from this point to this point. Abi? So I know that definitely x is going to be equal to r cos theta. Is it clear? If I want to get the y coordinate, I know the distance from here to here, I know that is going to be equal to r sin theta. Is it clear? So basically, if I want to go from this system to the other, the primary thing I need to know is, I need to know how x is defined as a function of the coordinates here, u, v, w. I need to know how y is defined as a function of u, v, w. I also need to know how z is defined as a function of u, v, w. Does it make sense? Is it clear?
No, I know.
Okay. So you need to know all of these, how they are defined for each of them, so that I will be able to go from this to this or from this to this. So I can switch between the two coordinate systems. So I need to know the definition of each one of them. So these are called transformation equations. Okay, that means if I want to go from the Cartesian coordinate system to the other coordinate system, I need to know what to call these transformation equations. Okay? Transformation. Okay, that's what you call all of this. Does it make sense? Just like if I want to go from XY, so from this XY coordinate system to the polar coordinate system, I'm going to have this now. I'm going to have x equal to r cos theta. You know, this is the same thing as writing x as the function of r and theta. Is it making sense to you? Is this clear? So this is a generalization that if I have three coordinates x, y, z, and I want to get them in the other coordinate system, I need to be able to define each of these terms as function of u, v, w. Is it clear? Just like in this case also, I can define my y as what? R sin theta. That means I'll be able to get y as a function of r and theta. So once I have these details, I'll be able to get other things I need from the coordinate system. Is it very clear? Is this clear? Alright. So one of the things you first have to know about this is, how do we define the, I'll get that please. How do we define the unit vectors? Okay, how do we define the unit vectors? You know, one of the primary things we work with are the unit vectors. Okay, we know that in our Cartesian coordinate system, unit vectors are I, J, K. How do we define the unit vectors in our new coordinate system? For instance, when we did MTH 104, you should remember we defined the unit vector ER and the unit vector E theta. Okay, can you remember anything like this? You wish. It is not teach you. They didn't teach us. Even the people like us say they didn't teach us. This life, yeah. People can be saying you at any time. Alright, good. So this is the idea. To get that, please pay attention, We know that so to go from one of them to the other, we will usually use the position vector. How is the position vector defined here? And see what will be the equivalence of it in the new coordinate system. So I know the position vector r is defined as r equal to xi plus yj plus zk. Making sense? I know this is the definition of this. And so, if I want to get, please pay attention, if I want to get the unit vector in the direction of I, for instance, or in the x direction, what I just need to do is to write something like this. When I differentiate r, this r vector, with respect to x, what do I get? I'm going to get this to be equal to del x, abi, I. This is going to give me I. Do you understand that?
Yes.
You get this? But if I do something like del R, del Y, it's going to give me J. If I do something like del R, del Z, it's going to give me K. Is it making sense? Is this clear? So that already gives me an idea that if I want to know the unit vector in the direction of a certain axis, I can differentiate the position vector and find out what will be the vector in that direction. Is it clear? Is it making sense? If I want to know the unit vector in a certain direction, if I want to know the unit vector in the x direction, I can differentiate the position vector with respect to x to give me the unit vector in the x direction. Is it clear? If I differentiate the unit position vector with respect to y, to give me the unit vector in the y direction. If I differentiate position vector with respect to z, to give me the unit vector in the z direction. Does that make sense? Yes. But now let's look at what will happen if we are using this coordinate system. Look at this. If I want to use this coordinate system, please pay attention to me. If I want to use this coordinate system, hello, listen please. That means my position vector r, which will be xi plus yj, will now be written as r cos theta I plus r sin theta j. Does it make sense? Do you understand this? So, in this case, if I want to know the unit vector in the direction of r, let me call it r cap. Is it clear? The unit vector in the direction of r. And I want to know the unit vector in the direction of theta, let me call it e theta cap. Okay, that means that should suggest that I should find out what then r will give me. Am I making sense? And what then r del theta will give me. Abi? So let's say, what are we going to get if we do all of that? We're going to have to be then r to be cos theta. And differentiate with respect to r. That will be cos theta I plus this with respect to r. That will be sin theta j. Okay? Then we find out, is it a unit vector really? Because it has to be a unit vector. Abi? So is it a unit vector? How do you find out if it's a unit vector? You find out what is its magnitude. Abi now? Okay. So what's the magnitude of this vector? 1. The magnitude of the square root of cos square theta plus I square theta is 1. So I don't need to disturb myself about it. I know that's going to be the unit vector in the r direction. Is it clear now? Okay. If I do then r del theta, what does it give me? Then r del theta is going to be what? That will be minus r, Abi, sin theta I plus r cos theta j. What will be the magnitude of this? Is this 1? To find out the magnitude, that will be square root of minus r sin theta all squared plus r cos theta all squared. Is it making sense? Yeah. So this is going to be what? Square root of, so I can move out the r square, Abi. That will be r into cos square theta plus sin square theta. Abi. So that was going to give us r. Is it clear? Is it making sense? It is going to give us r. That means that this vector, although it is going to be in the direction of theta, okay, it is not a unit vector. Does that make sense to you? Did you get what I just said? The first one will be in the direction along r, okay, and it will be a unit vector. Is it clear? As we saw it. But this one will be in the direction of theta, but it is not a unit vector. So that means that I will have to normalize it. To normalize it means I will make it a unit vector. Do you get that? And that means to do that, I will divide it. Don't forget something though. See, this ER simply means the unit vector in the direction of r. E theta means the unit vector in the direction of theta. Abi, what is guaranteed here is that this is going to be a vector in the direction of r, and we have established that its magnitude is 1. So it fits our definition of ER. That means this is what? The unit vector in the direction of r. That is okay. Is it making sense? Is this clear? Is this clear? Yes. But when you come here, I find out what is the unit vector in this direction. I know this is going to be a vector in the direction of theta. Is it clear? But it is not yet a unit vector. To make it a unit vector, I need to divide it by its magnitude. Is it clear? When I divide it by its magnitude, it will definitely give me a unit vector. Does that make sense to you? Yeah. Is this clear? So that tells us something that generally, if I desire the unit vector in the direction of u, for instance, I will simply write E sub u cap as del r del u divided by the modulus of del R del U. Do you understand this idea? Yes. Do you get that? When I take del R del U and divide it by its modulus, whether by its magnitude, that's what I mean by modulus. Whether that magnitude is 1 or greater than 1, do you get that? Or less than 1, it's going to give me a unit vector in the direction of U. Is it clear? Is this clear? Is this clear? Doesn't make sense to you. So that means generally, if I desire the unit vector in the direction of V also, I will simply do del R del V divided by the modulus of del R del V. Is it clear? Does this make sense? Is this clear? Is it clear? Is it clear?
Just dig. It's long.
Can we move on? So that means that in this case, for instance, molecular coordinate system, our ER, unit vector in the radial direction, is 90 units. Please write what you have in it. So look at it. So if you give me the unit vector in this direction, yeah, I'm saying that it's going to give me the direction, unit vector in the direction of R is going to be equal to cos theta I plus y theta j. So I want to get the unit vector in this direction, E theta is going to be equal to this thing. This is going to give me, what's this one? I have to divide by the modulus of R, the modulus of the vector, which is R. So it's going to give me minus sin theta I plus cos theta j. Is it clear? Yes. That will be the unit vector in that direction. So, that's exactly what that. So listen now. So the fact that I would need to divide this by something, listen very well. The fact that I will need to divide this by some modulus before I can have it as a unit vector in that certain direction, okay, means, in other words, that I will have to scale it, okay, by some factor before I can make it a unit vector. Is it making sense? So this denominator expression is called the scale factor. Is it clear? This denominator expression is called the scale factor. So a scale factor is denoted as H. So the scale factor for U is denoted as HU. The scale factor for V is denoted as HV. The scale factor for W is denoted as HW. Is it clear? That means scale factor here is written as modulus of del R del U. So when you see scale factor HU, it means modulus of del R del U. Scale factor HV, it means modulus of del R del V. Scale factor HW, it means the modulus of del R del W. Is it clear? Is this clear? Is this clear? Okay. Scale factor is clear. Scale factor is clear. Okay. No worries. I'm going to write what did you write now for both?
And I'm doing what to write.
Okay, this is what I mean by that. Listen now, listen. The unit vector in the direction of U will be given by del R del U. Del R del U normally will give you a vector in the direction of U. Okay? But for you to get the unit vector, you will divide by the magnitude of del R del U. Does that make sense to you? So this magnitude by which you are dividing before you arrive at the unit vector is called the scale factor. Is it clear? Yeah, scale factor of U. So H is equal to the modulus of del R del U. So that means that I can write EU as equal to del R, I can write it as 1 over H U del R del U. Do you know that? Yeah. I can write EV as 1 over HV del R del V. I can write EW as 1 over HW del R del W. Is it making sense? Is this clear? Yes, sir. Is this clear? Does this make sense?
Yes.
Okay.
Yeah, no, don't feel it like this.
to try something as assignment, that's what I'm saying. You're going to try it as assignment. So look at this. So pick up from there. I mean, the next class. So look at this, please. You know that, listen. This is for illustration. For the hello, it's okay. For the coordinate system we just look at now, for illustration, the polar coordinate system, where we have seen that x is equal to r cos theta and y is equal to r sin theta. Okay? Listen very well. Now, try to find out what your lambda. I know that lambda totally should be for our two coordinate systems. It should be equal to I del x plus j del y. Have you not? We don't have any c components, so let's say that will be there. Is it clear? So try to find out what will this be. If I want to transform it from this coordinate system to the polar coordinate system, what do you think it will be like? You get what I'm saying? Okay, for instance, you can write this as I del, this can be del R, then R del X. You know what I'm saying? So you can find out what this thing will give us. Polar coordinate system. If you want to differentiate this with respect to X, you know that instead of differentiating with respect to X, you know X has been defined as a function of R and theta. So we're going to find out that to differentiate that implicitly. We did that in what's it now? MTH 201, partial derivatives. So we want to differentiate with respect. We'll pick up from here.